Welcome back. In today's video, we're dealing with the phasor domain. And first of all, we want to say that KCL and KVL are valid in the frequency domain. This is important because it allows us to use all the analysis tools that is based off these two laws. And these include nodal mesh analysis methods, the Thevenin and Norton techniques, and several others. So we can go ahead and start from, in the time domain, Kirchhoff's law, voltage law, states that the algebraic sum of all voltages around a closed path containing n elements is equal to 0. So we can then write that as V1 of t plus V2 of t to the n of t is equal to 0. We can then go ahead and write V1 of t as the real part of the phasor counterpart of V1 of t times the complex exponential e to the j omega t plus the real part of the phasor component of V2 of t times the complex exponential, and last, the real part of the phasor counterpart of Vn of t times the complex exponential equal to 0. We can then go ahead, factor that, and we end up with the following: V1 plus V2 plus V of n e to the j omega t, and that is equal to 0. So as always, since e to the j omega t cannot equal 0, we can then set the real part of V1 plus V2, and these are the phasor counterparts, Vn equal to 0. So in our case, Vt, which is the real part of the phasor counterpart times the complex exponential e to the j omega t, the phasor counterpart is the time independent, and it is the phasor counterpart of the time dependent function v of t. So because this equals to v1 plus, and this is the phasor counterpart, v2 of v2, v of n equals to 0. So in the time domain, we have our KVL holding, and in the phasor domain, we have KVL holding. And this can go for I as well, so that means the phasor counterpart of I of t, I1, phasor counterpart of I2 of t, and phasor counterpart of I(n) of t. So both hold. So we have KVL and KCL. So both hold. So this states that KVL and KCL are valid in the phasor domain, which is very important. So the phasor domain analysis method consists of several steps. Thus, let's use the following example, which we have here, to introduce these steps. So let's ask, what is I of t? So we're going to find I of t for the circuit above. knowing the source voltage, knowing our angular frequency, and our resistance and our capacitance. So, step 1, we adopt the positive cosine reference. So instead of working in the time domain, we can obtain a desired solution by applying the phasor technique and avoid the sine and cosine function. So in the time domain, if we do a loop, we'll get minus Vs of t plus I of t times R, the voltage across the resistor, plus the voltage across the capacitor. That should be I of t dt, and that is equal to 0. So if we were to solve this in the time domain, this will be a lot harder. So let's adopt the positive cosine and transform to the phasor domain, solve for our variable, and do whatever we need to do. So the first thing, we adopt the cosine reference, or the positive cosine form, transform to the phasor domain, apply any known analysis technique to find your solution, then transform back to the time domain. So all voltages and current with known sinusoidal functions should be expressed in the standard cosine format, which is the positive cosine format. So for our problem, our source is the only time-varying quantity with an explicit expression and a sign. And since our source is given in terms of a sine function, we need to convert it to a cosine. So let's write this as step 1. So this is step 1. Put into cosine. So that means we're going to use the identity. Cosine of x is equal to plus or minus sine of x plus or minus 90. So then we can transform Vs of t, which is equal to 12 sine of omega t minus 45. Hope that's right. Yep. Which is equal to 12 cosine omega t, and minus 45 minus 90, we get 135, and that's in volt. So we have transformed our source voltage in a positive cosine. So now the phasor reference for V of t is, we can write that as 12 times the complex exponential e to the j minus 135. So step 2, we transform to phasor. So we can then transform our expression to the phasor domain. And we can do that by doing the following. So in our case, let's move our voltage to the right side. There it is. And then we can go ahead and also state that so we do not have a explicit expression, and we're solving for I of t, right? So because we don't have a explicit expression for I of t, or the phasor current, the phasor counterpart of I of t, so we do not have a explicit expression for I of t, nor the phasor counterpart of I of t. So we're in the phasor domain. So we can say step 3, Because step 2 is we transform to phasor, we can say step 3, we can use appropriate techniques and solve for unknown. So step 2 is above, which is here. Our capacitor, we know that in the phasor domain, it's 1 divided by j omega c, or minus j divided by omega c. We know that in the phasor domain, the impedance is R, impedance of our capacitor is here, and our voltage source, which is 12 cosine omega t minus 135, I think. Transformation to the time domain, we then get Vs, which is the phasor counterpart of that. So we can go back to that and start our step 3. So we can go ahead and say that I times R, IT times R. So the phasor counterpart of I of t is I times the impedance plus the impedance of the capacitor times, so that would be the current times the impedance of the capacitor, which gives us our voltage, and our source voltage, which is the phasor counterpart, V of S. We can then go ahead and write in our impedance for the resistor. Oh, I already put that down. I should have ZR. So here I would have I times R plus I times 1 over j omega c is equal to Vs. We can factor out the I because the I is what we're looking for. And yeah, let's factor out the I, and this is a 1 over j omega c equal to our phasor counterpart for source voltage. So we could have just transformed our equation from the time domain without even transforming the circuit. Once we get the equation for the time domain, which we have here, all we have to do is then transform this to this and then go ahead and work the equation. So let's go ahead, because we are solving for I of t. So here we have this in a form factor. We can then solve for I. So I is then our phasor counterpart of our source voltage divided by R plus 1 all over j omega c plus 1 over j omega c. We can then go ahead and simplify this a little bit, or massage it a little bit, I think a lot of people like to say. So we can multiply through j omega c. And let's just move to the other page. So if we multiply through by j omega c, we get j omega c times our phasor counterpart of Vs of t all over 1 plus j omega rc. Here we know that V of S is the complex exponential. So that's 12 times e to the minus j135, I think. Let's go look at that. Where is that again? Okay, there it is. So this is in the phasor domain. So we know that V of S is equal to that. So we also know omega, R, and C. So we can plug that in and simplify our expression, and we'll end up with 12 times the complex exponential e to the j90 times e to the j 135. That's 153. That's a 135. That's in degrees. And that is 2 times e. 2 times e complex exponential. E to the j is 60. Here, what we did, we convert to polar form because we needed to divide. And our numerator, we apply complex algebra. After we plug in our angular frequency, our resistance, capacitance, and VFS, we then simplify that and convert to polar form. And then in polar form, we're able to divide as soon as we can get the numerator in 1. So two complex, if we times a complex exponential together, we add the, so let's just divide out. So 12 divided by 2 is 6. And if we add 90 plus a minus 135 and then subtract 60 from that, so that would be negative 45 minus 60. So that would be negative 105. So that would be e to the j. So that would be minus 105 degrees. And that would be I. So here we have I in polar form. And as always, we can write that as 6 times the shorthand notation. And that's in ampere. So a magnitude of 6 and an angle of negative 105. So step 4 is then transforming our solution back to the time domain. And we can do that by using the relationship between time domain and the phasor domain. So a magnitude or coefficient. So a cosine omega t plus theta in the phasor domain is a times the complex exponential e to the j theta. So here we have I of t. So I of t is equal to, keep our a, so a is 6 times cosine omega t plus, and let's use our angular frequency. Where is that? So that's 10 to the 3. So that would be 10 to the 3 times t minus 105 degrees. And that's in milliamp. I forgot when I divide out from above, this is in milliamperes. And that's it for the analysis. So basically the fourth step is we adopt the positive cosine format. So whatever time dependent function, our expression, we transform that into a positive cosine format. And after we do that, we then go ahead and transform the circuit to the phasor domain, which we transform the impedances and everything over to the phasor domain that is dependent on time and so forth. And then step 3, we use any appropriate technique to solve for whatever is asked. And then after we do that, we then convert back over to the time domain by using the relationships between time domain and frequency domain. So the current in our series circuit is as follow, and basically that's it for this one. So I guess I'll see you in the next one. Bye.